Military installations like Tinker Air Force Base operate dozens of radar systems and high-definition security cameras simultaneously. This hardware creates a constant stream of sensor data, meant to provide a complete picture of the surrounding airspace. But the limits of that awareness are tested during a coordinated drone swarm event. As dozens of targets enter the airspace, every sensor on the base begins transmitting data at its maximum rate to the command center. Standard Ethernet networks treat all of this data as equal. In the fiber optic cables, massive packets of 4K video consume the available bandwidth, physically crowding out the tiny, time-critical packets containing radar coordinates. When network switches reach their capacity, they enter a state called buffer bloat. Critical tracking data is not necessarily lost, but it sits in a digital traffic jam, waiting for the high-volume video traffic to clear the queue. This delay has physical consequences. By the time a camera receives the command to slew to a specific coordinate, the target has already moved. The camera locks on to a patch of empty sky because the information it received was a second old. In these moments, the defender's unmanaged network becomes the primary point of failure. High-tech sensors effectively become blind spots because the data they produce cannot arrive in time to be actionable. PTCP-SARAHai addresses this by managing air domain awareness as a closed-loop network control problem. It creates a governed fabric that prioritizes the movement of physical state updates over bulk data throughput. The system architecture uses a dedicated fast path for what it calls P1 and P2 traffic. This is a reserved lane for track metadata and camera queue commands, ensuring these small, vital packets never have to compete with high-volume streams. High-resolution evidence and replay data are moved to a slow path. This keeps the bulk data flowing to the evidence vault without allowing it to interfere with the time-critical tracking updates required for live awareness. This chart shows the system's predictive control in action. While a standard network would hit the 100% saturation limit, the PTCP orange line stays below the 80% degraded threshold by forecasting sensor demand and adjusting the flow before the buffers can overflow. To maintain this margin during a swarm, the system intelligently shapes the data. It can crop full video streams into small regions of interest and delay background evidence replication, keeping the primary network clear for the tracks with the highest physical urgency. By governing the network based on the physical state of the targets, the system ensures that the most critical tracking information always arrives before it becomes stale. These charts compare the governed architecture against a standard Ethernet baseline during a 25-track swarm load. The results show an 80% reduction in metadata latency and a 97% reduction in critical packet drops. This reduced latency directly improves the queue-to-slew chain. Because the network queuing time is minimized, cameras receive coordinates and lock onto targets in under a second, allowing for immediate confirmation using optical flow residual tracking. For the operator, the result is this common operating picture. Instead of viewing dozens of disconnected video feeds, the system fuses radar and EO/IR data into a single display of active, uncertainty-bearing tracks. The interface provides track cards that summarize system confidence and sensor sources at a glance. On the bottom right, the priority lane bars show the operator exactly how much network capacity is being used for each class of data. This interface organizes sensor data into actionable track cards and group hypotheses. It allows a single operator to manage 25 targets across multiple sectors by prioritizing the physical state of the world over raw video throughput. The network physics that govern a military base also apply to civilian critical infrastructure. These bottlenecks occur in any environment where high-rate sensors meet constrained network bandwidth. At remote energy substations, security requires perimeter tracking, but these sites often lack the high-bandwidth backhaul to stream continuous high-definition video to a central office. In maritime terminals, the system correlates radar and camera data to track small craft among massive cargo ships, preventing the sensor network from being overwhelmed by the high volume of port traffic. At large venues, the AI manages incident evidence and local security workflows, ensuring that high-fidelity recording jobs do not interfere with the live situational awareness required during an event. Security in these dense sensor environments depends on a network that can distinguish between bulk data and physical urgency. By protecting track timeliness over total throughput, PTCP-SARAHAI ensures that the most critical information is never hidden in the noise.